Chapter 8, the giant planets. So beyond the orbit of Mars, the low temperatures of the solar nebula allowed condensing bodies there to capture hydrogen and hydrogen-rich gases. This, together with the vast amount of material in the outer solar system, led to the creation of the four large Jovian planets: Jupiter, Saturn, Uranus, and Neptune. It's composed mainly of gaseous and liquid hydrogen and its compounds, so these planets lack solid surfaces, and they may have cores of molten rock. The moons of the outer planets form families of miniature solar systems, although individually each moon presents a unique combination of size, structure, and appearance. So we'll start with Jupiter. It's the prototype of all the giant planets. It actually has more mass than the rest of the planets in the solar system all put together. Jupiter is more than 10 times Earth's diameter and 300 times the mass. You can see the size comparison over on the side. It has dense, richly colored bands or parallel cloud bands that cloak the whole planet. Jupiter is 5 AU away from the Sun, so it means it takes 12 Earth years to complete its revolution around the Sun. Its atmosphere is mostly hydrogen, helium, methane, ammonia, and water. Now it's really difficult to discuss the surface of the planet, since it's mostly a ball of gas. But we can define the surface as the cloud top, and so then we can say a few things about it. The temperature at the cloud top is very cold, about 200 degrees below zero. And the force of gravity there, if there was something to stand on, would be 2.5 times that of the Earth. So in other words, a 180-pound guy would weigh 450 pounds if he could stand at the surface of Jupiter. Now Jupiter is almost big enough to be a second star. If it had been 75 times bigger, which isn't very much in the scale of the solar system, it would have enough mass to collapse down and start thermonuclear reaction, which we'll talk about more when we get to stars. And we'd have a binary star system, and then anytime Jupiter was above the horizon, we'd have a second sun. Now the clouds on Jupiter appear to be particles of water, ice, and ammonia compounds. The bright colors of clouds probably come from complex organic molecules, or sulfur compounds, or maybe phosphorus. Now Jupiter rotates very fast around its axis. It rotates about once every 10 hours, and that fast rotation speed leads to a very significant equatorial bulge. In other words, it is much wider than it is tall. Remember, it's easy for gravity to collapse things down this way, but when it's spinning around, it's very hard to collapse it this way. Similar to if you're on the merry-go-round again. It's very easy to stand up and down, very hard to pull yourself into the center when it's spinning fast. Now if we look at the interior of Jupiter, its average density is about 1.3 grams per cubic centimeter. That indicates its interior is composed of very light elements. Now the interior becomes increasingly dense with depth, and the gas turns to a liquid hydrogen about 10,000 kilometers down. And deeper still, the liquid hydrogen compresses into liquid metallic hydrogen, similar to mercury. And this is a material scientists only recently have created in very tiny, high-pressure diamond cell chambers. Now, there probably is an iron rocky core a few times bigger than the Earth at the center, but this is one of these areas that we're unsure of. Now, Jupiter's core temperature is about 30,000 degrees Kelvin. That means it emits more energy than it receives, and it's probably due to heat left over from its creation. And the planet may still be shrinking in size, so it converts gravitational potential energy into heat. Now there's a convection pattern on Jupiter. So deep in the interior there's a lot of heat, so that is carried up to the top of the atmosphere in the gas. That high altitude gas then radiates energy into space and it cools and sinks. So hot material rises to the top of the atmosphere and spreads towards the pole and the equator. Now, since Jupiter is rotating, there's a Coriolis force, and that turns the rising and sinking gases into powerful jet streams that move about 300 kilometers per hour, and we see them as cloud belts. So as the gas comes up from the center, it's pushed one way. As it sinks down to again, it's pushed the other way. So I get bands of gas going opposite direction all along Jupiter. Now, adjacent belts have different relative speeds, and they create vortices of various colors. The largest, of course, is the Great Red Spot, which has persisted since Galileo's time. He was the first one, of course, to look at Jupiter through a telescope, and he noticed the Great Red Spot. We can measure the velocities of different bands. This band up here moves about 270 miles per hour. This one towards the center moves about 220 miles per hour. Down low in the southern half of Jupiter, it only moves about 90 miles per hour. So all the bands move different speeds and have different energy. Now, the Great Red Spot is essentially a hurricane. It's a storm system that's been churning on Jupiter for at least hundreds of years. Like I said, it was first seen by Galileo in 1610. It's much like the hurricanes formed on Earth, but is many times bigger than the Earth itself. Earth would fit very nicely 3 times inside the Great Red Spot. Now, convection in the deep metallic liquid hydrogen layer, coupled with the rapid rotation, creates a magnetic dynamo just like we have on the Earth, except it's much bigger. The magnetic field is about 20,000 times stronger than the Earth's field. It's the largest planetary magnetic field. And because of that, you get auroral activity and intense radio emissions from the magnetic field. This is a picture taken of Jupiter, and you can see up at the top and the bottom the aurora, similar to what we see on the Earth. The magnetic field also traps charged particles far above the planet in regions similar to the Van Allen belts. And this picture here, you can see these dots here. This is lightning occurring in the clouds of Jupiter. Now, why is Jupiter's atmosphere so different from Earth's? The crucial factor here is escape velocity. So, for a planet to keep an atmosphere, the speed of the gas molecules, which will denote V sub mol, must be less than the escape velocity, which will denote V escape. Now, different molecules have different weight. So, for example, a hydrogen atom has a weight of 1. Hydrogen gas, H2, has a molecular weight of 2. Helium gas, molecular weight of 4. Nitrogen, N2, 28. Oxygen gas, O2, 32. Carbon dioxide is 44, and so on. So every molecule has a different molecular weight. Now, from elementary physics or thermodynamics, we can show that the molecular velocity of an object depends on the temperature and the molecular weight of the gas. In other words, the molecular velocity of a gas is proportional to the square root of its temperature over the molecular weight. So the higher the temperature, the faster the molecules are moving. But at a given temperature, the more weight you have, the less velocity you have. Now, earlier we talked about escape velocity, and we said that the escape velocity of an object is the square root of 2 times Newton's gravitational constant times the mass of the planet divided by the radius of the planet. So Jupiter has a very high mass and a very low temperature. And that means that the molecular velocity is much less than the escape velocity, whatever the molecular weight is. So therefore, Jupiter has an extensive atmosphere of hydrogen and helium. Compare this with the Moon or with Mercury. They have very high temperatures during their days, but very small masses. So that means for these objects, the escape velocity is larger than the molecular velocity for all the common gases, so they have no objects in their atmosphere. The other terrestrial planets, say Mars, Earth, and Venus, are somewhere in between, and different molecular weight gases behave differently. For the heavy gases like oxygen, nitrogen, and CO2, The molecular velocity is less than the escape velocity of these gases and are retained in the atmosphere. However, low molecular weight gases, such as hydrogen gas or helium gas, have high molecular velocities which actually exceed the escape velocities. Therefore, the terrestrial planets can't hold on to their helium or hydrogen that escapes into space. Any helium balloon that you have at, say, a birthday party or whatever, when that balloon pops and the helium escapes, it moves up to the top of the atmosphere, and then those atoms at the top of the atmosphere have escape velocity, and so they escape out into space.